Okay, now that you have the background, we're going to start the step 5 script. I've downloaded it from the website. You should too. If you haven't at this point, just pause the video and go get that script. And of course, I'm working in my RStudio project for the course. So I'm going to open this step 5 script and I'm going to do the usual sort of thing here. I'm going to go to Edit, Folding, Collapse All, and take a look at the code chunks that we're dealing with, so the bones of this script. And there's a lot here. And again, there's a number of things we're trying to accomplish, many of which I'm going to gloss over the statistics of it and direct you to outside material to learn more about that. The introduction to the script, the goal is to identify these DEGs and DTUs, situations where there's differential transcript usage. You should already know going into this script, if you're analyzing your own data, you should already know what the pairwise comparisons are that are of most of interest to you. You should also know if there are variables that you may want to control for while testing for those differences, like batch or patient number. We're going to, whether you look at differential expression at the gene or transcript level is really going to depend on how you read that Callisto data into R. Obviously, today we're going to be doing that at the gene level. And then I sometimes I forget to say this, and I always get questions about it. If you happen to have your own data and you have no biological replicates, you really can't do any of the things we're going to do in the script today. And that's because the ability or the process for finding differential features, genes, transcripts, whatever, between conditions requires replicates, right? These are ultimately statistical tests. And so having an N of 1 is not appropriate in this case. Does it mean you should throw your data out? Of course not. There's many cases in the literature where people have, done large screens with microarrays or RNA-seq across many different samples or conditions where it's just not experimentally feasible or financially feasible to do 2 or 3 replicates for each condition. So they do a large screen and then they focus in on differences and validate those, right? That's the key thing, is we're worried about false positives when we do a limited number or no replicates. And so we need to absolutely then validate that. And so if you have no replicates, the way you would be moving forward at this point would be to use dplyr and the tidyverse tools that we talked about already to generate fold change columns that you could then sort and find your top sort of mover. So you'd be operating basically only on fold change and not on any sort of p-value or false discovery rate. Okay, so that's all the intro. The packages that we'll load today are already mostly familiar to you. Tidyverse, Lima. You don't have Lima yet. We haven't used it. So go ahead and download and install that package. It's a bioconductor package. EdgeR, you've already used, DT, GT, DT, and Plotly. So really just one new R package. All right, and that then brings us to the first task at hand, which is always one of the hardest for me to kind of explain, which is that we're going to set up a design matrix. And this is not to be confused with the study design, although the study design is an important part of setting up the design matrix. So let's just discuss this for a minute. I want to make sure that you understand that just because you have a study design file, which we've called targets, and we'll just take a look at that. Just because you have a study design file does not mean that the choice of comparisons is inherent from that study design file. There's nothing about this that tells me exactly what pairwise comparisons I should make. Now, to us, based on what we've discussed thus far, you can anticipate that this is going to be a disease versus healthy comparison, but that is not implicit in the study design, the study design file itself. So we need to now actually articulate that. We need to be explicit about what the comparisons or what the experimental design is. And to do that, we're going to use the model matrix function. Okay? Now, before we do the model matrix function, we're going to capture the variables of interest from our study design. We've done this now in the Hackdash. We've done it before in the course. The idea is that we're going to dip into that targets file and grab the variable we're interested in this case group, and turn that into a factor and assign it to the object group. And of course, we are already familiar with what that does. It shows our character vector of length 10, but it also then shows that these have levels to them, 2 levels, disease and healthy. And that's the sort of structure we want going into this model matrix. Now, the model matrix function ends up being an essential part of how we're going to then set up our and apply a linear model. So if you want to learn more about the linear models, first, I guess if you want to learn more about model matrix, I provided a link in the reading material today to thinking about different kinds of model matrices. I would also direct you to the Lima or EdgeR manuals. They have extensive sections on setting up different kinds of model matrices to control for things like batch effect, to block on patient if you have repeated assays or paired measurements across the same patient, treat blood pressure before, blood pressure after some drug, for example. And so there's many different experimental designs that we can create with the model matrix, but it's not always evident how to do that. But there's a lot of documentation out there. The Lima manual, the EdgeR manual, and other links that I provided in the reading material. For the purposes of today, we're going to set this up in a way that is, I think, quite commonly done, which is to say I want no intercept for my model matrix. So tilde 0 means no intercept. And I want to be able to do comparisons across this variable group. All right, so let's, before we talk about this anymore, let's actually run this line of code and see what kind of object is created by model matrix. So I will now run the design and just take a look. And I can see that it's really recognized that there are 10 samples. So this is the way the model matrix produces an experimental design from the information you give to it. I can see that it recognizes that I have 10 samples, and it's created 2 columns here. One called group disease, because the variable is group and the value is disease, and one called group healthy. And it said it's also assigned those 10 samples to those groups. Now, you may look at this and think, well, that doesn't look really all that different from what you have here, where I have the first 5 as being healthy and the next 5 as being disease. But it is different. Here, this is a column of basically characters, healthy and disease. Here, those are variables where we have a 1 and a 0. These are assigned in a way that makes a linear model now possible. But you'd be right that this information is also encoded in here. All right, if you were to have a batch effect, or desire something called a blocking design where you might have a paired analysis, there's very easy ways to do that using the model matrix, where you can, instead of setting no intercept, you can set an intercept to something like a block or a batch, and then test for the effect of treatment after setting your intercept to that. So the bottom line is this model matrix is the critical way of establishing and setting up how you're going to apply a linear model. All right, I don't like these column names of my model matrix. So I'm going to, just like you would with any sort of data frame, I can take anything and put it into the column names of that design. So I'm going to use the levels function, which recognizes the levels of any factor. And I'm going to take those levels, which is actually a character vector of length 2, and use that to rename the columns of my design. Okay, so I ran that, and now if I highlight design and I evaluate that, I see now I have these just easier column headers of my design. And why does that matter? Is it just for aesthetics? No, it matters because later and very soon, I'm going to need to call on these different columns of my design to do my pairwise comparisons. And it's just going to be easier for me to do if they have names that make sense to me. All right, so I've added some notes here about how you might want to change this model matrix line of code depending on your study design and what you're trying to ask. But ultimately, this is the first place in our analysis where we've actually started to articulate the kinds of comparisons and covariates that are of interest. All right, so now that we've done the model matrix, we are ready to do something else that's sort of maybe odd or unexpected to you, and that is to try to model this mean variance relationship. Remember, in the presentation that I gave you in the first part of the lecture, I said there's increasing development in ways to kind of improve our ability to detect signal over noise, and I mentioned Callisto's bootstraps as one new tool for that. But another is this idea that we talked about again at the beginning of the course about this mean variance relationship and the fact that no matter what we do, RNA-seq data has this heteroscedastic quality to it where there is unequal variance across a range of increasing means of gene expression in this case. And so we try to deal with that a little bit by log2 converting things, but that doesn't totally fix the mean variance relationship. So the Lima package has a function called voom, which will variance stabilize your data. In other words, it will model the mean variance relationship. So it'll observe that mean variance relationship and fit a model to it, and then apply precision weights to each gene depending on how it fits that mean variance relationship. So the function for doing this is voom, as I said. We're going to give to voom our DGE list that had been filtered and normalized. All right. We're going to give it our design, which was the design matrix we just made. And then we're going to tell it we want it to plot the mean variance relationship because I want you to actually see what this looks like. And I'll remind you before we run this that this DGE list contains our samples, right? How deep we sequenced each library. It contains normalization factors now because we did normalize using the calc norm factors. And then it contains, counts, right? And that's, I guess, maybe something I haven't mentioned yet is that all of these differential expression tools, Lima, EdgeR, DE-seq2, they all take counts in as the base data that they work with and that they apply statistical models to. And that's because that's what all these tools were built around, were counts, not around TPMs or FPKMs. So we should always, and we've already done this, that's why there's counts here, we should always be feeding Lima, EdgeR, DE-seq count-based data. All right, so we understand what this DGE list is, but now we've applied this voom function to it. So we're going to go ahead and do that. And it doesn't take long to do, and it's going to produce a plot here that will show us that mean variance relationship. And that'll display in just a second. And then we'll take a look at, let me go over to plots, there it is. So here's the mean variance relationship for each gene in my data set. Each gene is a dot here with its log2 expression on the x-axis and the square root of the standard deviation on the y-axis. And I can see, when we've converted to log2, that we've skewed things so that lowly expressed genes tend to have a slightly higher variance, and it's fit aligned to kind of model that behavior. And as a result of that modeling of the mean variance trend, it's now changed our DGE list, and I just add a V in front of it to indicate that it's variance stabilized. And if I take a look at that DGE list, let me just run this again. Here we are. Okay. I can see that now I have a new element in that list called weights that wasn't there before if I had looked at this. And those weights are precision weights applied to each gene, each row, in each sample, each column, that help to apply or use this mean variance trend to improve our ability to detect differentially expressed genes. All right, and that's linked in today's reading material as well on the course website, how this voom function works. All right, so now we've taken these extra precautions, right? We've modeled the mean variance relationship, we set up the model matrix, and we are ready now to fit a linear model to our data. If you and I could stand myself to take linear algebra. I haven't, but if you have and you're familiar with linear models and least squares, that's what's happening here. Again, check out the lecture page for a sort of breakdown of linear models and least squares in more detail. But we need to give linear model fit our normalized, filtered, variance stabilized DGE list, this thing we just created, and our design, right, the thing that was produced by Model Matrix, and it will fit a linear model to our data. So we'll run that now. It doesn't take long, but it's not instantaneous, so we give it just a minute. And then the next thing that we're going to do is we are now going to start to choose the pairwise comparisons that we want to make. And to do that, we're going to use a function from Lima again, and linear model fit is from Lima as well. We're going to use a function called make contrasts. And contrasts here is just another word for comparisons, pairwise comparisons. All right, so the lm fit finished running. And if you take a look at that fit object we created, it's got a number of different elements to it. You can see the method used was least squares. It's got pivots, degrees of freedom, residuals, sigma, a bunch of stats stuff that we're just not going to dig into now. Okay, so we have fit a linear model to our data, and now we want to extract that linear model fit for the variables or comparison of interest. And so we're going to use the make contrasts function. We're going to say that we have really one comparison, and we get to name that how we want to refer to that. We're going to call it infection. But now we have to actually articulate what that pairwise comparison is. And we're going to say it's disease minus healthy. And we need to tell it where it should look for those sort of assignments. So let's remember that our design here, right? Our design has disease and healthy as the column headers. We have to use column headers from our design in this make contrast function. Now our design is really simple. It only has these two conditions. If you have more complex designs, which is easy to do, or just more variables, maybe maybe your group was not disease and healthy, it was disease 1, disease 2, disease A or B, and then and so you have multiple columns. So you would have to choose the columns that you want here. All right, single pairwise comparison. If you had a second pairwise comparison you also wanted to make contrast to deal with, you could put that here, right? And you could say this is a genotype equals wild type minus knockout. Again, these would have to be in your study design to be able to be used. But you can have as many contrasts or pairwise comparisons here as you want, and that will then give you the ability to identify genes that are different between, in this case, disease and healthy in my data set. All right, so I have make contrast set up. I've given it my design. I'm ready to run this part, and I can now take a look at that contrast matrix and all of that work to make a simple matrix where it's saying, listen, you've got a single contrast called infection. That contrast has two levels, disease and healthy, and you want to take disease minus healthy. All right. Now the actual orientation of these, whether I switch these around and put healthy first and disease second, has no meaning or no bearing on the analysis per se. It'll just change the sign of genes that come out as being differentially expressed. And I do want to caution you just to think or recognize the order that you put yours in for your studies, because you want to think whether there's a certain intuitive order to these that will make sense to you. So for example, I put disease first because if there are genes that are elevated in these patients with cutaneous leishmaniasis, I would like those genes to have a positive sign to them. I would like them to be highly upregulated if they're higher in a disease state. Okay, versus if I had disease over here and healthy here, things that were higher in the disease state, right, than healthy would have a negative sign. So you just want to be aware of the orientation there. Okay, now that we've set up our contrasts of interest, we've applied a linear model to our data, we are ready to use that contrast to extract the linear model fit using that contrast. All right, so we'll run that bit. And now we've overwritten this fits object, and you'll see it's still populated with a lot of stats here that again, we're not going to get into. But then we can get Bayesian statistics for our linear model fit. They end up being really critical for us in understanding which genes are differentially expressed. All right, so we run eBayes on the extracted linear model fit, and we'll call that eBayes fit or EB fit. And at this point, we now are done. The differential gene expression is done. We have statistics for all of our genes for the pairwise comparison that we expressed that we were interested in. I included a line of code commented out here in case you choose to write those statistics out. If you want to see all the stats, you can use write fit and then point it to the EB fit object you created, assign that to stats, and you could take a look at it or save it to a file. But at this point, we want to actually start to look at our differentially expressed genes, right? It doesn't feel like we finished differential gene expression, but we did. So now we want to actually, take advantage of what we've done and really take a look at things. So we are going to use we're going to start off with one really useful function from Lima that will let us just look at the differentially expressed genes in our console here. And that's called top table. Just as the name suggests, lets us look at the top differentially expressed genes based on our pairwise comparison and sorted by any statistic we want. So top table needs a couple things. It needs these eBay stats that we pulled out of the linear model fit. It needs to know how you'd like to adjust for multiple testing. We'll talk about that in just a minute. It needs to know which coefficient or contrast you want. This is synonymous with contrast. Our contrast matrix, of course, only has one contrast, and that's called infection. And so we can only choose coefficient number one. There's only one to choose. What if you had multiple? How would you know which is which? This is always the first one. The second one would be right below it. The third below that, etc. So you know from when you did your make contrast what the coefficient number is. We only have one. If you were to put 2 here, it would throw an error when you ran it. And then we want to say how many genes we want returned. Let's not do 40,000 right now. Let's do 10. And then we have to say we're going to have a number of statistics presented to us as a table. We have to articulate how we'd like these top 10 genes returned. Or should they be the top 10 based on log-fold change? Based on adjusted p-value? What would we like? So we're going to do log-fold change. We're going to hit run. And we're going to take a look at this my top hits. And now we see the first insight we have into statistical evaluation of differential gene expression. And for this data set, ranked by log-fold change, here it is, the most significantly changed gene is matrix metalloprotease 1, MMP1. We actually saw that even already just in doing our kind of dplyr, making a log-fold change column with no statistics, right? We were still able to find that as being really, really strongly upregulated in patients with this disease. And then we see a ton of immunoglobulin light, heavy chain, kappa chain genes here as indicating some sort of B cell response in these patients. We have a p-value for each of these comparisons. So MMP1 compared between disease and healthy, very small p-value. But remember, we're doing multiple tests here. We're doing a test each time we have a gene. We are testing for whether it's significantly different between disease and healthy, and that repeated tests makes us vulnerable to type 1 errors, that is, false positives, thinking a gene is differentially expressed when it's not. In fact, if we're trying to test at a p-value of 0.05, we can actually understand that 5% of the time we may have a false positive or interpret a gene as being differentially expressed when in fact it was not. Now, that may not seem like a high frequency, but 5% of the time with large data sets where we have 10,000, 20,000 genes is a substantial number of genes that would come up as being differentially expressed even if there was no differential expression at all in our data set. So to help control for this, we use multiple testing correction. That's a general term to refer to a way to adjust these p-values to account for these repeated tests. We use a particular method, Benjamini-Hochberg, which is indicated by the BH. You can choose other methods if you'd like, but that's the common one for multiple testing correction with gene expression analysis. And I linked to a Benjamini-Hochberg multiple testing correction video if you want to learn more about how these adjusted p-values are generated. When they're generated using Benjamini-Hochberg, they are, you can call them adjusted p-values. You can also call them false discovery rates. And you can see that in general, they are all higher than the p-values. So that's the first thing to notice is, these p-values will take a hit but we really want to focus on this adjusted p-value or FDR, not the p-value column, all right, because these have not been corrected for multiple testing. These have. All right, so that's great. We can also convert this my top hits into a tibble. We know how to do that, and then we can use GT to make a table out of it and just look at it over here as well. Yeah, there it is. Okay. So that's fine. I've got additional explanations here about the B statistic and the T statistic column, B and T. If you have any questions about that, where B is the log odds that a gene is differentially expressed, and I give you an idea of how to think about that and how to calculate the log odds that a gene is differentially expressed, and then the T statistic I've described here as well, just for you to take a look at. All right, so you should understand log fold change and average expression, of course. You should understand the p-value, and after it's been adjusted for multiple testing by Benjamini-Hochberg. The T statistic and B statistic I almost never or never refer to in papers really, but again, you have an explanation here of what that is if you want. So now you understand how to pull out any number of top genes ranked by any of these statistics that you'd like using the top table function. All right, in the next part of the video, we're going to actually use this top table function in a creative way to then produce a volcano plot. We'll pick up on that next.